Morning to all. Today I will discuss thin pressure vessels. So thin pressure vessels are generally closed cylindrical or spherical container designed to hold or store fluids at a pressure higher than the atmospheric pressure. The stored fluid exert pressure on the container, and due to which basically three types of stress are generated in generated in the surface of the thin pressure vessels, and these are longitudinal, circumferential and radial stresses, which we are going to discuss in the upcoming slides. And these pressure vessels are used in refinery industry and petrochemical industry. So generally the pressure vessels are categorized into thin pressure vessels and thick pressure vessels. Thin pressure vessels are categorized based on their diameter to thickness ratio. Whenever the diameter to thickness ratio is more than 20, it is called as thin pressure vessels. When the diameter to thickness ratio is less than 20, then it is called as the thick pressure vessels. If we will see for the examples of thin pressure vessels, then LPG cylinder, pressure cooker, storage tank, boiler cells, these comes under the category of thin pressure vessels. And whenever and when we will go, if we will go for the thick pressure vessels, then hydraulic cylinder, storage tank, whenever we operate it at a high pressure, and then we and the ratios of diameter thickness are also maintained less than 20, then we will call it as a thick pressure vessels. Generally, two types of shapes are mostly preferred due to ease in manufacturing and transportation, and mostly cylindrical type of pressure vessel is mostly preferred. Although both cylindrical and spherical type of pressure vessels are used in today's world. There are different types of cylindrical pressure vessels available in today's. So the type first includes the pressure vessels which is composed of only metals. Second types of pressure vessels are available in today's market, in which the liner is composed of metals while the outermost layer is composed of glass fiber reinforced composite materials. The third types of cylindrical pressure vessels includes in which the liner is made up of aluminum metal, while the while the topmost layer is composed of carbon fiber reinforced composite material. And in the type 4 types of cylindrical vessel consist of liner consist of plastic, generally is a HDPE are used as a liner, and carbon fiber reinforced polymeric composite are used as the topmost layer. So these are the four types of cylindrical pressure vessel mostly available in the market. So in thin pressure vessels, the stress distribution throughout the thickness will not vary significantly, and it is assumed uniform, or we can say it is constant throughout the thickness. For a closed cylinder with an internal pressure, there are three types of direct stress act upon it. First one is longitudinal stress in the x direction, or second one is the hoop stress in the circumferential direction, and third one is the radial stress which acts radially outward. So the stress, the longitudinal stress, the direction of longitudinal stress is parallel to the axis of the vessel, while the direction of the hoop stress is perpendicular to the axis, or we can say it is tangential to the circumference. While the radius stress, the direction of radius stress is along the radius from inside to outside of the wall. The radial stress in a thin cylinder is small enough, and it is ignored for thin pressure vessels. Its magnitude is very small, hence it is neglected. So coming to the now we will see the calculation of longitudinal stress. Whenever the thin pressure vessels when it is used to when fluid is stored inside the container, the fluid exert a pressure. Suppose the fluid exert pressure P. So we are considering here only in the axial direction. So the stored fluid will exert pressure P in the axial direction. So we will take a cross section, and then we will see that due to pressure P, the stress will be developed, and the stress will act on the circumferential area. And this circumferential area is nothing but it is 2 pi r, and since it consists of the thickness T, so this stress sigma L is acting on the circumferential area 2 pi r, and if we will and if we will consider for the thickness, then the thickness is T. So if we will equate the force in the x direction, then we can write it as sigma L is acting on 2 pi r, so, that area into T, and pressure is acting on the circular area pi by 4 into d square, or we can also say it pi r square. So after equating, we will obtain sigma L from here, and we can say that the sigma L is equal to PD divided by 4 into T. Similarly, if we will go for the circumferential stress, so we will take a cross section. We will take a cross section parallel to the x-axis, and we will observe that the sigma C is acting on the two surfaces, and the length and this length will be L, and the thickness is T. So sigma C is acting on two surface. So and pressure is acting over the length L, and we will go for the rectangular portion, then the area is length into breadth, and width here the width will be the diameter D. So we can say that first we will equate the forces in the y direction, and we will observe that sigma C is acting on the length L into T, and this is and there are two such areas, so it is 2 into L into T, and the pressure P is acting on the rectangular portion, that is length L and diameter D. Diameter D is nothing but acting as a width here, so P into DL. So sigma C is equal to PD divided by 2T. Again, so we already know sigma L in longitudinal direction and sigma C in circumferential direction. So if we will observe the two stresses, so PD by 2T and PD by 4T, we observe that from these two stresses, the sigma, the maximum stress observed is PD by 2T. So sigma max is written here as PD by 2T. So again, if we will consider the shear, though if we will calculate the maximum shear stress in plane, then the formula for maximum shear stress in plane is sigma 1 minus sigma 2 by 2. So we will put the values of sigma 1 minus sigma 2 divided by 2, then we will obtain it as PD by 80. Again, if we will observe the max tau max, then it is sigma 1 minus sigma 3 divided by 2, and sigma 3 is 0 here, neglected, so it will be obtained as sigma 1 by 2. Again, so we will write sigma 1 by 2, it means PD divided by 2T divided by 2, it means it will be as PD by 4T. So again, we will calculate the strain. So so the formula for longitudinal strain is sigma L divided by E minus Poisson's ratio into sigma C by E. So we will put the respective values of sigma L and sigma C, and we will obtain the longitudinal strain as PD by 4T into 1 minus 2 into mu. Mu is nothing but Poisson's ratio. Again, the circumferential strain is obtained by putting the respective values of sigma C and sigma L here, and we will obtain the circumferential strain as PD by 4T into 2 minus mu. So again, volumetric strain will be calculated by adding the strain in x, y and z direction, and the z and now we know that the strain in y and z direction will be same. So finally it will be a longitudinal strain plus 2 times of circumferential strain. So we already know, we have already evaluated the longitudinal strain and circumferential strain. So we will put the value here, we will add it here, and we will obtain the volumetric strain. So again, now we will see we will see the spherical type of thin pressure vessels. Now, since in cylindrical pressure vessels, the stress generated along the longitudinal direction and along the circumferential direction are different, but in spherical type of pressure vessels, due to symmetry in nature, the stress developed in each and every direction will be same. So here the longitudinal stress will be equal to the circumferential stress, and so now we will see how we will evaluate or how we will derive the circumferential or longitudinal stress here. So we will take a cross section, parallel to the y-axis, and we will observe that due to pressure sigma c will be developed. So sigma c will developed on the circumferential area 2 pi r, and suppose its thickness is t. Now we will equate the forces in the x direction. Then we will observe that sigma c is acting on the circumferential area 2 pi r into t, and p is acting p is acting on the circular portion pi r square, or it can also be written and the pi r square can also be written as pi by 4 into d square. So from here we will get the sigma circumferential stress PD by 40, and in a spherical shape of pressure vessel, sigma c will be equal to sigma longitudinal stress because stress will be due to symmetry in nature, sigma c will be equal to sigma L. So tau max, as per the formula, tau max in plane tau max will be sigma 1 minus sigma 2 by 2. Here both sigma 1 is equal to sigma 2 is equal to sigma L is equal to sigma c, all are equal, so it will be 0. And tau max will be sigma 1 minus sigma 3 by 2. Sigma 3 is 0 here. Sigma 1 is PD by 40, so PD by it will be tau max will be PD by 80. So again we will evaluate the strain terms, and strain will be circumferential strain according to the formula sigma c by E minus Poisson's ratio into sigma c by V. Now we will use the values of circumferential stress, and we will obtain finally it as a PD by 4TE into 1 minus Poisson's ratio. Again, to evaluate the volumetric strain, Ex plus Ey plus Ez, so all the terms for a spherical type of pressure vessel, Ex will be equal to Ey equal to Ez, so we can simply write Ez 3 times of circumferential strain. So we already derived the formula of EC, so we will directly use the formula of EC and 3 times of circumferential strain, and we will get the volumetric strain. That's all. Thank you.